So today we'll be discussing about polar plots. Polar plots are in fact the base of Nyquist plot. So once you know how to draw polar plots, it becomes very easy to draw the Nyquist plots. And in order to understand the stability and the relative stability of any system, so it is in fact Nyquist plot that you will require for the system. As the name suggests, polar plots are the plot of polar coordinates. So you learned about polar coordinates in the form of r theta. So in this case, if suppose that you are given a magnitude of any system, let's say ms, so that could be any function which would be represented as s plus a, s plus b, and so on, divided by s plus p, s plus q, and so on. So polar plot of ms is nothing but the plot of magnitude of ms and the phase angle of ms on polar coordinates, as omega is varied from 0 to infinity. So this is very similar to the r theta plot. If suppose that so in this particular case, what you are going to do is you are going to find m, the magnitude of m. So this magnitude of m is evaluated, this becomes r, and the phase of m will become theta. And since m is a function of s, so after putting s equal to j omega, so if you suppose you put s equal to j omega, so this is something that you had been doing for all type of frequency domain analysis. So you first convert the transfer function into frequency function. So this gives you the frequency function, as mj omega. So from this mj omega, what you do is you compute the magnitude m and phase phi, and since these two quantities are the function of omega, so once you vary omega from 0 to infinity and you plot this on a two-dimensional plane by varying omega from 0 to infinity, so you will observe a locus of these points. So if suppose that I say for omega equal to 0, the point I got was this. So this is m, this is m and phi for omega 0. And let us say I evaluated m and phi for omega equal to 1, and the point I got was somewhere here. So this becomes m and phi, this is m phi for omega equal to 1. Likewise, let's say I then evaluated a point for omega equal to 10, and I got that point somewhere here. So this is the point that corresponds to m phi for omega equal to 10. So what I actually am doing is I am computing r and theta. So this is r theta or m phi for omega equal to 0. This is r theta for m phi omega equal to 1. This is r theta for the polar coordinate m phi for omega equal to 10, and so on. So I will keep on doing this from omega equal to 0 to omega equal to infinity, and suppose that the final point corresponding to omega infinity I got is somewhere here. Now what I will be doing is I will be tracing all these points, which are nothing but the what I'm going to do in polar coordinate is going to trace the locus of these points. So if I trace the locus of these points, so this graph, this particular graph is termed as polar plot. Now again, there are certain set of rules that are required to draw polar plots, and these rules will be discussed step by step now. So the steps that are required for drawing polar plots are: the first step is to obtain the transfer function or the frequency function in the time constant form, which means that if suppose that you're given the frequency function of this form, s plus k into s plus a into s plus b and so on, divided by s plus p into s plus q and so on. So you are first required to convert this into time constant form, which means that this thing will be converted in the form of k dash 1 plus sta into 1 plus stb divided by 1 plus stp into 1 plus stq and so on. So this particular expression is termed as the time constant form. So after converting this into time constant form, the second step follows is to substitute s equal to j omega, which is something that we had been discussing right from the beginning of this unit, that you, after converting any transfer function, or you will have to convert the transfer function into frequency function. So this will give you the frequency function m of j omega. So your expression, this equation, then turns out to be k dash 1 plus j omega ta 1 plus j omega tb divided by 1 plus j omega tp into 1 plus j omega tq and so on. So you obtain the frequency function of the given transfer function. So these are the two basic steps which were involved in all type of frequency domain analysis approaches. For example, you did the same thing in Bode diagram, and if you remember the PowerPoint that I uploaded, I have written there are two basic steps that are involved in all the frequency domain approaches, and these were the common steps which are to be applied in almost all frequency domain approaches. And the different frequency domain approaches differ with respect to each other in terms of the steps that follows these two. So the subsequent steps 3, 4, 5, whatsoever you're going to have, depending upon what frequency domain approach you're going to use, will be decided by that approach. So step 3, 4, 5, 6 are different for Bode plot, and these steps are different for polar plot. And again, if you're going to draw Nicholas chart, then you will be having different steps. So step 3 in polar plot is to now compute the magnitude of m at 2 points. So you are going to compute, so there will be two parts in this. So first you will have to compute limit omega tending to 0. Oh, I forgot the third step. The third step is to first convert mj omega into the magnitude part, and you will have to separate. The third step is to first separate out the magnitude part of mj omega and angle or the phase of mj omega. So you're required to convert this into this form. So this becomes the third step. This is also common in all the procedures, all the frequency domain approaches. The fourth step says that you will have to compute limit omega tending to 0 magnitude of mj omega. So now what you're doing is you're using this term, and you're going to compute this term by putting limit of omega tending to 0, and so you're going to compute this value at omega equal to 0. Likewise, you will have to compute limit omega tending to 0 phase of m. So you're going to use this value, this expression, to compute the phase. So this is, what is this? This is the magnitude of m at omega 0. Likewise, this is the phase of m at omega equal to 0. Then again, the fifth step says that you will have to compute the values of magnitude of mj omega and phase of mj omega at omega infinity. So if you compute limit omega tending to infinity magnitude mj omega, so this will give you the magnitude of m at omega infinity, while limit omega tending to infinity phase of mj omega will give you the phase angle of mj omega at omega infinity. So what you're basically trying to do using step 4 and 5 is you are trying to find the 2 points of the transfer function at omega 0 and omega infinity. So which means that if I try to locate this on the two-dimensional plane, so I'll be having, let's say I got mj omega, the magnitude, with an angle of let's say I got this value as 5 and this was 0. So I got this as 5, the angle was 0 degree, and I located this point on the two-dimensional plane. So the point that I obtained at omega equal to 0 is this, and the other point I obtained was let's say m equal to 0. So suppose that I computed this limit omega tending to infinity magnitude and I obtained this as 0, while limit omega tending to infinity angle of mj omega was obtained as minus pi by 2. So that point will be 0, angle minus pi by 2 will be somewhere here. So this is the value that I got for omega tending to infinity. So by these two steps, what I'm trying to do is I'm trying to find the two ends of the curve, the polar plot, because the polar plot will be starting, as I told you, that what you're going to do is you're going to vary omega 0 to infinity. So what I did was I computed this limit and this limit. So I obtained the two ends of the curve and located this on the two-dimensional plane. And again, I inform you that polar plots drawn by hand are again approximated plot. So in order to draw polar plots, what you are going to do is you're simply going to find the intercepts with the axes. So now what I know is that my plot is going to start from this point when I vary omega from 0 to infinity. So suppose that I got this particular point at omega 1, then this point at omega 2. So I came up with an information that the plot is going to move in this direction, and this is going to come to an end at this particular point. So I came up with two values at omega equal to infinite, the values of magnitude mj omega and angle mj omega, that was 0 and minus pi, so minus 180 degree. So this particular information minus pi gives me an idea that the curve will be approaching to this particular magnitude 0 from an angle of minus pi. If this value would have been minus pi by 2, so in that case the curve would have approached this particular point from minus pi by 2 axis. So these are the two ideas that I get from step 4 and 5. Now the sixth step follows. So in step 6 you will have to split the function mj omega into real and imaginary part. So you're going to split this function into real part and the imaginary part. So how are you going to do this? I'll explain this part, this step, when I'll be doing a related question. The next step is to obtain the frequencies at which the plot intersects the real axis. So I'll be computing the values of omega for which there are intercepts, the graph intersects the So if there exist intersections with the x-axis and y-axis, then I'll have to compute the value of frequency corresponding to these intersections, and this will be computed by setting the real axis. So in order to compute the intersection with the real axis or the imaginary axis, let us assume that for intersection of the curve with the imaginary axis at this point, so we know that the real part of this mj omega at this particular point is 0, because this is completely imaginary. So we'll be having only expressions of terms like j of, let's say, x. So in order to compute this particular point, which is the intersection with the imaginary axis, I forgot to mention the imaginary and real axis. So these are imaginary, this is imaginary axis, this is the real axis. So to compute this point, since this point corresponds to only imaginary content of function mj omega, which means that the real part of mj omega should be equal to 0 point. Alright, so at this particular point you will be having real part of mj omega as 0. It will be 0 at this particular point. So for obtaining this intersection, or for obtaining the value of m at this particular point, what we are going to do is we are going to set m, real part of mj omega, equal to 0, which will give the intersection of the plot or the curve at imaginary axis. Likewise, for obtaining the intersection with the real axis, we'll have to set the imaginary part as 0, which means that we'll be setting imaginary part of m j omega equal to 0 to obtain intersection with the real axis, if it exists. So these are the two steps. So this is 7 of A and this is step 7b. So you'll be performing these two steps separately in order to compute the values of omega corresponding to the intersection at imaginary axis and at real axis respectively. to obtain the value of mj omega at the intersection at imaginary axis and real axis, you will have to put the values of omega corresponding to these points thus obtained from 7a and 7b. So substitute, the next step says substitute, let's call this step as 8. Substitute the values of omega obtained in step 7. And where are we going to substitute this? So there are two options you have with this. One is that you substitute the value of omega right into mj omega and this particular expression. So you're going to get a value if it is corresponding to intersection at imaginary axis, then putting the value of omega, this value of omega into mj omega will give you only the imaginary part. In order to perform lesser computation and to get the answer in few steps, better idea is to put this value of omega, whatever you obtained, into imaginary mj omega, because we know that this omega will give the real part of mj omega, will make this part and real part of mj omega as 0. So it's better to put the value of omega obtained for this intersection directly into imaginary part, because we know that imaginary part is going to be having certain value here while real will be 0, and this will make our computation steps. So we'll be performing lesser computation if we do so. So steps 8 says substitute the value of omega obtained in step 7. So we are going to substitute this. So to obtain, so this will be having again two steps. First is to obtain the value of mj omega at imaginary axis. So substitute omega from step 7a to imaginary mj omega. So this will give you the intersection or the value of mj omega at frequency which you obtained from step 7a, which was nothing but intersection at the imaginary axis. Likewise, for step B, you will be obtaining the value of mj omega at real axis by substituting omega from 7b to real part of mj omega. So let me write this for you. Let's forget about this. So unit of B is obtain the value of mj omega at real axis by substituting omega from 7b into real part of mj omega. So let us say we have a function given as ms equal to 10 upon s into s plus 1 into s plus 2. So we are required to draw the polar plot of this function. So if we follow the rules that we just studied, so rule number 1 says to first ensure that this is given in time constant form. Since you see this function is not given in time constant, you will have to convert this first into time constant form. and this can be done by taking out the constants from within inside the bracket. So this becomes 1 plus s, you take out 2, so you can write 2 here, 2 into 1 plus 0.5 s. So this becomes time constant form of the given transfer function. Then the next step says to substitute s equal to j omega in order to find the frequency function. So you get mg omega as 10 over 2 j omega multiplied by 1 plus j omega 1 plus 0.5 j omega. So this is the required frequency function of ms. The third step then says to separate out the magnitude function. So magnitude of mj omega can be obtained the way we learn in Bode plots. So this can be written as 2 omega under root 1 plus omega square into 1 plus 0.5 omega square. And the phase of mg omega or phi can be obtained as, so the same way that we learn in Bode plot, this can be assumed to be 10 plus j0, this can be assumed to be 0 plus 2 j omega. So the angles corresponding to each of these terms can be computed as, from numerator you will be getting positive angles, tan inverse of 0 upon 10. From denominator you will be getting negative angles, so tan inverse of 2 omega upon 0 minus tan inverse of omega upon 1 minus tan inverse of 0.5 omega upon 1. So tan inverse of 0 is 0, tan inverse of infinity comes out to be minus pi by 2 minus tan inverse of omega, then minus tan inverse of 0.5 omega. So now we came with these two elements which will be required to compute the Bode plot. Now the fourth step says to calculate limit omega tending to 0, magnitude m j omega. So if you substitute omega 0 in this particular function, you will observe that this comes out to be 10 divided by 0 and all finite, then this becomes infinite. Likewise, if you compute limit omega tending to 0, the phase mj omega or phi, so you're going to substitute omega equal to 0 in this particular function. So if you substitute omega 0, this becomes tan inverse 0, which is 0, tan inverse 0, this is again 0. So you only get minus pi by 2, minus 90 degree. Now again, in the next step, you compute limit omega tending to infinity, magnitude m j omega. So you substitute infinity in this particular expression, you get this value as 0. And for limit omega tending to infinity, phase mj omega, if you substitute this value into this particular expression, so minus pi by 2 minus tan inverse of infinity is minus pi by 2, minus tan inverse of infinity is again minus pi by 2. So minus pi by 2 minus pi by 2 minus pi by 2 will give you minus 3 pi by 2. The sixth step says to split this function into real and imaginary part. So if you look at this particular expression, in order to convert this mg omega into real and imaginary part, let's rewrite this. Mg omega was given as 10 over 2 j omega 1 plus j omega 1 plus 0.5 j omega. So in order to split this into real and imaginary part, what we are going to do is we are going to multiply with the expressions with the complex conjugate of expressions of these type. So we'll multiply and divide by the complex conjugate of this term and this term. So we get as 10 over 2 j omega into 1 plus j omega into 1 plus 0.5 j omega. Then this will be multiplied by 1 minus j omega, the complex conjugate of this term, and the complex conjugate of this term, 1 minus 0.5 j omega divided by 1 minus j omega, 1 minus 0.5 j omega. So now this reduces to, so I'm not going to write each and every step in what we, so I leave this up to you. You evaluate, you find the intermediate steps, and I'm going to write the expression directly. So the real part comes out to be minus 30 divided by 9 omega square plus 2 minus omega square whole square, and the imaginary part comes out to be minus j 10 into 2 minus omega square upon 9 omega cube plus omega 2 minus omega square whole square. So we came up with two expressions. This part corresponds to the real part, well this is the imaginary of. Now the seventh step says to find the intersection with real and imaginary axis. So in order to find the intersection with real and imaginary axis, what we are going to do is we are going to compute the each of these terms, real put to 0 and imaginary put to 0. So if we put real part of mj omega equal to 0, so we are going to compute this minus 30 upon 9 omega square plus 2 minus omega square whole square equal to 0. So this will give us values omega equal to infinity. Likewise, if we substitute, so this was part A, and seventh, if we talk about part B, so part B says that if we substitute imaginary part of mj omega equal to 0, which is nothing but this expression minus 10 2 minus omega square upon 9 omega cube plus omega 2 minus omega square whole square equated to 0. So this gives omega equal to plus minus under root 2. So the unit will be radians per second. Now next step is to use these values in order to compute the value of mjj omega, which will correspond to the intersection to real and imaginary for values of 7b and 7a respectively. The 8th step is to use the value of m omega equal to infinity, and we'll put this value into imaginary part. And one thing to notice here is that instead of computing omega equal to infinity again, because we did this thing in step 5 where we computed limit omega tending to infinity, magnitude as well as angle. So I think there is no need to compute this step again. So we already did this in step 5. So for omega equal to infinity from step 5, we saw that we saw that the magnitude was 0 while angle was minus 3 pi by 2. For step 8b, so now in this case we are going to compute the magnitude mjg omega and angle. Sorry, we are going to know the values of mjg omega for omega equal to plus minus root 2, which is what we got for the intersection corresponding to real axis. So if we put this into this part, the real part, so what we are going to get is m j omega for omega equal to plus minus root 2, m j omega comes out to be equal to minus 5 by 3. So now we are going to plot the graph using the values that we computed. So this should ideally be done on graph paper. I don't have it right now, so I'll be explaining this on this board. So this is the imaginary axis, this is real axis, and I have a marking, let's say, of centimeters 1 2 3 4 5 6 1 2 3 4 5 6 1 2 3 4 5 6 1 2 3 4 5 6. Now the first from step number 4 and 5, what I saw that corresponding to omega equal to 0, I had magnitude as infinity and angle as minus pi by 2. So infinity, so minus pi by 2 is the angle which will be taken clockwise from, if you assume this to be the reference axis, we call this as a reference axis. So from this reference axis, the angle minus 90 degree will be taken clockwise. So minus 90 degree corresponds to this line, and the magnitude is infinity, which means that the curve will be coming from infinite at an angle of minus pi by 2, since the magnitude is infinity. So this curve will be coming from infinity, which corresponds to omega equal to 0. The second point that we computed in step 5 was corresponding to omega equal to infinity, and the magnitude for this was 0 while the angle was minus 3 pi by 2. So magnitude 0 corresponds to the origin, that is this point, and the angle minus 3 pi by 2 gives the idea that how the curve approaches this particular point. So we know that this is corresponding to infinity and the magnitude is 0, while the curve will be approaching from the minus 3 pi by 2 axis. See, we got two information. So one thing that we conclude from these two information is that the curve will be intersecting the real axis somewhere at this point. So if we now look to the rule 7, so from rule 7 we get the values of intersections, which was 0 for the case when omega was infinity, and the intersection for omega equal to plus minus root 2 was minus pi by 3. So this is going to be on the real axis. So we mark the intersect this minus pi by 3, which is approximately equal to minus 1.667. So minus 1.667 will be somewhere minus 1, minus 1.5, and minus 1.667 will correspond to this point. So the intersection will be somewhere at this point, which is, this corresponds to omega equal to plus minus root 2. So this is all the information that we needed to plot the root locus, and thus joining all the 3 points that we obtain starting from omega equal to 0, which comes from infinity, and crosses this particular intersection and meets the origin at this point. So this is the required polar plot.